Okay, in today's video, I'm going to go over how to use the thin lens equation for calculations of image height, image distance, size, and orientation for a concave lens. This is our problem. We have an object, it's 8.5 centimeters tall. It's placed 11 centimeters from a concave lens, and this concave lens has a focal length of 6 centimeters. And again, we want to know where will the image be, how big will it be, and what will its orientation be. And this is the information that we've been given, so I like to write it all down. And it's important to note that this says concave lens. Concave lenses have negative focal lengths, all right, by convention, and therefore we have to put down a negative. We got to make sure we carry that negative through all of our problems. The object distance is 11, and the object height is 8.5, and of course we want to get the image distance and the image height. And I think before you begin, it's very good to just pick up your pen or pencil and make a quick sketch on your page. Now I'm doing this in Keynote and it looks nice and neat, but I just don't even pick up a ruler or make anything to scale. I just make a quick sketch on my page. I put F and 2F down on both sides. I write down maybe concave lens, so that reminds me it's a concave lens. And I think to myself, okay, if I put the object out here, okay, where should the image be? Now you should know this based on what you've learned about lenses and mirrors already and what the ray diagrams you've done. You know that if it's a concave lens and the object is here or really anywhere, then the image will always be between the lens and F. So the image distance has to be less than 6. The image will always be smaller than the object. So that means the image height has to be less than 8.5. And we know that it will always have the same orientation, so that means my magnification and my image height has to be positive. And of course, it will be a virtual image. Okay, so we know it'll always be there, and hopefully when we do our calculations, we'll get those same types of answers that will indicate those things. Okay, so let's go through and do the problem. Once we wrote everything down, we're going to get the image height first. We're going to use the thin lens equation, 1 over F equals 1 over DO plus 1 over DI. Now we want to solve for the image distance first. So we're going to subtract 1 over DO from both sides. That means we get 1 over DI equals 1 over F minus 1 over DO. And now we can just plug our numbers in. And it's important to remember that we're going to write down 1 divided by negative 6 minus 1 over 11, because we said concave lenses have negative focal lengths. Convex lenses have positive focal lengths, but concave lenses have negative focal lengths. We got to take this negative through and carry it through all of our problems. Okay, so now you can simply do this on your calculator. 1 divided by minus 6 minus 1 divided by 11. If you have a standard kind of graphing calculator, then you'll get that the 1 over the DI is equal to minus 0.258. Now remember, and a lot of people have a problem with this, this is not the DI. This is 1 over the DI. In order to get the DI, we have to take the reciprocal of both sides. That means we get DI equals 1 over negative 2.58. All I did was I flipped this up, so to speak, and I flipped this up because this is really 0.258 over 1. So I just flipped it up. I get DI over 1. I don't write that over 1 down. DI equals 1 over negative 0.258. And all I do in my calculator is go 1 divided by negative 0.258 or negative 0.258, and I get that the image distance is minus 3.88 centimeters. I think, okay, that's great, because we said it has to be less than the focal length. The focal length is 6. The image appears inside the focal length, inside the focal point, and that's 3.88, and negative means it's on the same side as the object. So far we feel good. We have the correct image distance. Okay? All right. Let's go on. We can write that down. Let's go on and get the image height. Now to get the image height, we have to use the magnification equation. The magnification equation, or one of them, the first one we're going to use, is the magnification is equal to minus DI over DO. It's important to use this minus sign. That means the magnification is equal to minus negative 3.88 divided by 11. You can see we have a minus sign here and a minus sign here, and that basically means it's a minus divided by a minus, or negative divided by a negative. And that means if we divide that out, we get that the magnification is positive 0.353. Now I didn't write the positive down because usually we don't, but it's important to note that it is positive. That magnification is less than 1. That means the image is going to be smaller than the object, and once again we feel good about that because we know with a concave lens the image must be smaller than the object. Now we can go through and use the other magnification equation, which is that the image height divided by the object height is equal to the magnification. And we're going to solve for the image height. We want to solve for this. So we're going to kind of cross multiply. We get the image height is equal to the magnification times the object height. We know the magnification, we know the object height. We can just plug the numbers in, and we get that the image height is +3. So the image is going to be 3 centimeters tall. The object is 8.5 centimeters tall. The image is smaller than the object. We know, once again, with the concave lens, the image has to be smaller than the object, and therefore we feel good about that. This is +3. That means it has the same orientation. If it was -3, it'd have the inverted orientation. This is +3, which we don't really write that down, so I didn't write it down. But it's important to note that it's positive, and that means the orientation is the same as the object. It's smaller, and that is good. So once again, write all that down. Now let's just go through and look at our diagram we made earlier and see if it matches. The image height, image distance is -3.88. Well, that fits because we said it has to be less than 3. Excuse me. We said it has to be less than 6, and that is less than 6. We also said it has to be smaller. The image is smaller. The image is 3. The object height is 8.5. We said it has to have the same orientation. Well, the image height is positive. That means it has the same orientation, and that means we get a virtual image also. Okay, so everything fits. We feel good, and we know that we probably did the correct work and got the correct answers. Okay, so hopefully you found that helpful. I think if you go through, follow the steps, go step by step, write everything down, think about your lenses and mirrors and what you're using and all your negatives and positives, and go step by step, you'll be successful. Okay, if you found that useful, please let me know. Give me a comment in the bottom or give me a thumbs up, and we will see you next time. Thank you very much.